Great job on the preview exercises. Don't forget that in your folders today, you should have project 1. And on the back table is your packet for the next series of classes that will go for, from Monday through your test number 2. You can pick that up on your way out if you didn't pick it up on the way in. Don't forget, you have a take-home quiz today. It's due Monday. You have your first exam on Wednesday. And I will, on Monday, try to quickly grade those quizzes, and I'll have them available if you want to stop by my office either Monday late afternoon or Tuesday. I'll have them done definitely Tuesday morning. So if you want to stop by and get them, that will be fine. I will also give you, I will send you through Moodle an answer key so you can look at that if you can't get in here on Tuesday. So I'll put the quiz solutions on Moodle so that you can compare, you know, or look it over before Wednesday. So let's take a look at today's topic. It says other types of equations. So what 2 types of equations have we looked at so far? Quadratic and simple ones, which are called what? Linear, right. So we've looked at linear and quadratic. So today, the strategies that we use to solve linear and quadratic equations, we're going to be using them today, but sometimes we have to apply some other strategy first before we can start applying the strategies that we know pretty well. So today we're going to look at several categories of equations. And so for you, you'll want to make sure that when you look at an equation on your homework or on a test next week, you can categorize it. This type of equation is called a polynomial equation. Well, you say, so wasn't a linear equation and so wasn't a quadratic equation. Those are all examples of polynomials because the powers that you see are all positive integers in this case. 2, 3, and 4. You don't see any fractions like you had to work today on your preview exercises. And you don't see any negative powers. So these are actually going to be a lot easier to solve than equations that would have negative or fractions in them. So the idea here is, what can we borrow from the equations that we've learned to work so far? What ideas can we borrow? And we're going to borrow the idea of the zero product principle, which says if you multiply 2 things that equals 0, one of those things is 0, or in some cases they could both be 0 if they're equal. But any number of factors that you set equal to 0, this principle is still going to hold. If I had that expression, then I know either A is 0, B could be 0, or C could be 0. So this is the idea we're going to borrow from quadratic equations, where we just have 2 factors to help us with polynomial equations. So polynomial equations use the idea of factoring, and guess what? They're all going to have a common factor. So the factoring technique that's going to be useful here is your greatest common friend. And then this zero product principle suggests that in order to solve these, we have to set the equation equal to 0, whatever it is. So that's your first step. You want to set your equation equal to 0. And in this case, I'm just going to subtract 6x squared from both sides. And then when I rewrite my equation, the standard procedure is to always start with the highest degree and move on down to your lowest. So it goes, the degree of this first term is 4, to the third, and to the second. So we've already used the zero product. Well, we haven't created a product yet, because in order to create a product, we need to factor, because product means the end of a multiplication problem. So that's where your greatest common factor comes in. Your greatest common factor is x here. X squared, thank you. So you pull x squared out. Notice you have 3 individual parts to this adding and subtracting problem, which means you must have 3 spots inside. And we call those spots terms. So x squared times what gives me x to the 4th power? What am I missing here? What would I have to, x squared, right? Because we want these to be equivalent. And x squared times what gives me x cubed? X. And then what would my final term be here? 6. Okay, because I've already got the negative sign there. Okay, and again, I want to reinforce that every time you solve an equation by writing an equivalent equation. You always keep your equation all the way down. Don't leave off that 0, because if you leave off this 0, then there's no way to solve this. It's just an expression. So don't get into bad habits, and if you've already established them, it takes literally 1 second more to write equals 0. Okay, it's not going to create a whole time snag for you. All right, now are we done? Well, you say x squared can't be simplified anymore. It's prime. What about this second factor here, x squared plus x minus 6? Are there factors of 6 that differ by 1? Are there factors of 6 that differ by 3 and 2? So that's how I can quickly factor that. I create my 2 binomial, and I say x times x, and I know it's 3 and 2, but I know one has to be positive and one has to be negative because it's a negative 6. So which one's going to be negative? 2, and 3 is positive, because when I add those, I get the plus 1 that's right here. So I put x plus 3, x minus 2, and it doesn't matter which order I put those factors because multiplication is commutative. And now I have 3 factors. So I set each one of these factors. So again, notice I'm going to keep reiterating this. This is an equation. And now I'm going to create 3 equivalent equations from this equation right here. 3 equivalent equations. And they're baby equations. They're the ones that Marco said were simple. X squared equals 0, x plus 3 equals 0, and x minus 2 equals 0. You create those 3 equivalent equations and you solve all 3. And most of the time they're going to be linear equations, not always, and if not, they'll be quadratic, and you can solve those. So here we get x equals 0. What do we get for this one? X equals what? Negative 3, and x equals 2. So notice even your solutions are equations also. So you start off with a complicated equation and you keep whittling it down with equivalent equations using different strategies. How would I write this in my math lab in a solution set? What order would I write, Sam?
Negative 3, 0.
Right. So remember, my math lab wants you to put the smallest number up to the largest in that order, left to right. Okay. For me, you can just write it like this. This is fine. Any questions on the procedure, how you think about it, any of the steps that we did so far? Anything at all? Okay, let's move on to the next type of equation we're going to be looking at today. Radical equations. There's a radical in the equation. They're really easy to notice, to put them in their category of radical. There's no like surprises, or you just see something with a radical and you say, okay, it's one of those radical equations. So the idea that we borrow from solving linear equations is when we solve linear equations, we say we want to get our variable term on the one side and our constant term on the other. The same idea goes here. We want to get just our radical term all by itself on one side of the equation and get rid of anything that's hanging around it, whether it's being added or subtracted to and from it, or multiplied or divided. So you look at this equation and you want that square root of x to stay right where it is. You want it to be isolated all by itself. So what do we got to do here to just have that sitting there all by itself? We want to subtract x, right? So we subtract x from both sides, and now we get this square root of x equals 12 minus x. All right, so we've done that first step. Now, if you recall that when we solve a simple equation like this, we're so used to doing it, we don't even think about it anymore. But what we're really doing when we solve an equation is we're performing inverse operations because we want to undo the addition of 5 because we want to get that x all by itself. And to undo adding 5, we subtract 5. That undoes it. So we get x on this side because it brings us to 0, and we get 5 on this side. So now we want to use the same idea, and we want to undo the square root. So what process undoes a square root and gets you right back to x? Squaring it, right? So now you want to square both sides. Whatever you do to one side of the equation, you must do to the other. Okay, and there we go. Now I'm all set, right, Marissa, to put those little slashes through there because it's just the square root of x. So since they undo each other, it brings you right back to what you started out with. Originally, you had an x, you took its square root, and now you're squaring it. And guess what? You've done a round trip. You're right back to x. And this is the only part. I'm hoping that by the time you all leave Math 107, you'll know how to square a binomial, and nobody will write 144 plus x squared here. It's 12 minus x times 12 minus x, which gives us 144 minus 24x plus x squared when I multiply that out. So we've borrowed some ideas for solving linear equations by inverse operations. When you look at that equation that's sitting right there, what kind of equation is it? Quadratic. So now we can go back and use the strategies that we use to solve a quadratic equation. So we know we have to set this equal to 0 because the only way we can use a quadratic formula is when the equation is equal to 0. That's how we created it. So we get 144 minus 25x when I subtract x from both sides, plus x squared. And all I'm going to do is rearrange these from the highest power down to the smallest. And that's usually the way we're used to looking at these trinomial expressions anyway, so we can factor it. So now we're looking for factors of 144 that add up to 25. That's 16 times 9. Excuse me? Because I subtracted 1x from both sides. So we get 0 equals x minus 16 times x minus 9 when I factor it. And if you couldn't figure out those factors, you could always use your quadratic formula. Anytime your answers are rational numbers, you know you could factor it. You set each factor equal to 0. Remember, you're always solving equations. Always, always, always. And your picky math teacher will take off if you don't continue to have equations all the way down. X equals 16 and x equals 9. But before you go putting circles around these, you must check. Because you took something that was a square root and you made it into x to the first power. And often you'll get an answer that doesn't work. We call that extraneous. So you have to always go back to your original equation, which you probably forgot by now, but it was x plus the square root of x equals 12. And if you check both of these, you can put 9 in plus the square root of 9 equals 12. So this is what you're checking. And 9 plus 3, hey, cool, that works. Yep. And now you try your 16. 16 plus the square root of 16, does that equal 12? Nope. So this solution is what we call extraneous. And this is the only solution. So when you put your solution set into my math lab, that's only one element in your set, the element 9. Okay. So these radical equations borrow the techniques you already know to solve them. The thing that's different is the idea of undoing your radical. So in this case, we squared both sides. What if the radical had started out being the cubed root of x? What would I have done to undo the cube root? I would what? Would I square a cube root? Would that undo it? You'd raise it to the third power, right? Whatever, because what you're doing is you're trying to get an exponent of 1. So let's look at that a little bit here. So when you have the square root of x and you square it, let's see what's really going on. We know we can write square root of x as an exponent. It's x to the 1/2 power. That says the same thing. And what do we do right here? What exponent property do we apply right here when we have a power to a power? What do we do with the 2 and the 1/2? We multiply them, right? Since 1/2 and 2 are reciprocals of each other, when you multiply them, you just get the number 1, which is x. So that's really what's going on when you do that little slash there, is you're taking 1/2 times 2, and you're getting the exponent of 1, which brings you right back to x, which is where you started, okay? So if we had a cubed root, getting back to the question I just asked you, the cubed root would be written like this, 1/3. So to undo the cubed root, you'd have to put an exponent here that would bring you back to 1 when you multiplied that number by 1/3, and that's its reciprocal. The reciprocal of 1/3 is 3. You'd cube both sides. So whatever the exponent is, you just raise that radical to a power that's the reciprocal of that exponent. In this case, it was 1/2. We used 2. Okay. All right, so now that was leading into equations with rational exponents. There's a little typo here. I want you to change this right here on your sheets from rational to radical. Okay, rational to radical. Do you have a question, Dan, that I can help you with? Do you have a question, Dan? The one we just did? Okay, what's the question? I'll be glad to help. You're all right? Oh, okay. All right. All right, so fix this on your paper. This should be changed from rational to radical. Okay. Again, how do you recognize an equation with rational exponents? You see a fractional exponent. And you have two choices here. If you like working with radical equations, you can convert this to a radical. Or we can use the idea we just saw a minute ago. We want to raise this to its reciprocal power to get x to the 1. However, before you do any of that, you've got to get x to the 3/4 all by itself. You don't want to be raising this to any powers now, because that's going to get really ugly fast. So you want x to the 3/4 all by itself. So think of this problem as 3x take away 6 is 0, just at the beginning. If it was 3x take away 6 equals 0, what would be the first thing you would do? You would divide first? All right. So if it was 3x minus 6 equals 0, what would you divide, Blake? Oh, so the first thing you would do would be add the 6 over? Okay, sorry, I didn't hear that part. Sorry. Okay, add 6 to both sides, okay? All right, so again, when life gets complicated, try to simplify it. If you look at something and you're not quite sure what to do, turn it into something you would know what to do with. 3x minus 6, I can handle that. I'd add 6 to both sides. Guess what? It doesn't change. So here you would get 3x equals 6. What am I going to get on this side? Over here with this, 3x to the 3/4 equals 6. Okay. Okay. Now, let's think over here. What would I do with 3x equals 6? You're on, Blake. Oh, no, we're over here on this simple one first. What would you divide what? Yeah, divide both sides by 3. Yeah, that's what we would do if it was a baby linear equation, and we'd be all done. Unfortunately, we won't be all done here. So we're going to use the same technique here. We want that x to the 3/4 to have a 1 in front of it. And so we get x to the 3/4 because this is our well-chosen 1. We've chose that 1, 3 over 3 equals 2. Now here's the part where we have more work to do. And this is totally up to you how you approach this. You have to undo two things. You have to undo the cubing of x and the 4th root of x. You can do it in 2 steps or you can do it in 1 step. It doesn't matter to me. So let's see. We could say, I want to get rid of that fraction first. So you could multiply both, raise both sides to the 4th power if you wanted. And when you do that, those 4's cancel because 3/4 times 4 over 1 is the same as 3. So I get x cubed equals 16. Now you have to undo cubing something by taking the cubed root. You can either do it as a radical or as an exponent. That creates a 1, and you get x equals the cubed root of 16, which you can write like that, or you could write it like this. They both say the same thing. That's 2 steps. A minute ago, we saw that we could create x to the 1st power by raising whatever expression we had, whatever the power was, we raised it to the reciprocal. So when we had the square root here, when we had 1/2, we squared both sides because that's the reciprocal of 1/2. When we had 1/3 here, we cubed both sides. So you don't have to get all freaked out because there's a number other than 1 in the numerator. You can still find the reciprocal of 3/4, which is 4/3. And you can raise both sides to 4/3, and that takes care of it in one fell swoop. Because when we multiply 3/4 times 4/3, we get 12 over 12, which is just 1. All of this cancels and becomes 1. So there's our x, which is what we always want at the end. And here's our answer, 2 to the 4/3. Okay. And you can write that as 16 to the 1/3 or the cubed root of 16. Or you could leave it like that if you wanted. It's okay with me. Well, it's not a question of solving it because this is the solution. What it means is sometimes you'll get an answer here that you can simplify to like a friendly number, which is rational, and sometimes it isn't rational, like this is an irrational number. So the only thing you could do other than writing it this way is if I said approximate your answer and you'd put it in your calculator and get some estimate. But sometimes you'll get an answer. That's why we were working on all of this earlier, Blake. Sometimes you'll get an answer which you can simplify. Sometimes you get an irrational. And now that we're graduating up to Math 107, sometimes our answers look a little uglier than they did in our other classes. We leave it just like that.
So okay. Either would be acceptable?
Yes, either is acceptable. If you can't simplify this, you could leave it like this for me. Or, now, well, actually, I have to undo what I just said because we can simplify this. So all the work we've done with radicals like this, we kind of chickened out and used square roots by finding a factor that's a perfect square, right? And we do this. Is there any way to factor this so that I get a perfect cube that divides into 16? 8 and 2, right? So I could do this. The cubed root of 8 is 2, and I can't simplify that anymore. So this can be simplified further. Let me show you how that works here. Look at this exponent, 2 to the 4/3. I'll show you how it comes out to be exactly this. Do you agree that 2 to the 4/3 is equal to 2 to the 3/3 times 2 to the 1/3? Because when I multiply, I keep my base the same, and what do I do to my exponents? You add them. So 4/3 can be broken up into 3/3, which is 1 plus 1/3. And what's 2 to the 3 over 3? It's just a baby 2, and this is your cubed root of 2. So either way, you get exactly the same answer, whether you just look at your exponent. What a lot of students do is they say, when they see a power here that's an improper fraction, and if you recall, an improper fraction means your numerator is larger than your denominator. What happens when you divide 4 by 3? What do you get? Yep, you get a decimal. What mixed number is it? 4 divided 1 and 1/3. Look at your exponent. 1 and 1/3. So it's 2 to the 1st times the cubed root of 2. Huh? Oh, snap. Yeah. So sometimes you get something that is not rational. Most of the times I hope to try to keep your answers something you can simplify, like the stuff you did in your preview exercises. But you want to try to expand your algebraic skills a little bit now and be able to go, even when they're not as familiar, like cubed roots or fifth roots, you can still apply the same ideas. Yep, Sam?
So for an acceptable final answer, we choose cube root 2,
Yeah,
not 2 to the 4/3.
yeah. Let's just say if you can get 2 to the 4/3 and you don't simplify it, I'm not gonna take anything off. I might show you. I would love to see you, reduce this further. But if it's something you can simplify to a rational number, I definitely want to see that. I don't want to cause you any anxiety, right? But it's a nice skill to have, to see that you can simplify cubed roots as well as square roots and fifth roots and whatever root you have. It's all the same idea. Okay, do we have any more to look at? One more. And then you're going to be set free to do whatever you want. All right. So look, Caitlin and I, when we talked about this, we created this little saying here that here's an absolute value equation. Again, you see the absolute value sign. This is the simplest kind you can have because there's nothing multiplying it on the outside. There's nothing being added or subtracted. It's not being divided by anything. The absolute value is already isolated on the left side in this particular case. And your constant is on the right. So remember, the absolute value of stuff, no matter what kind of stuff expression is inside those absolute value, if the absolute value of stuff is equal to some number, then that means the stuff inside is either equal to the number or its opposite, because we know the absolute value of opposites is the same. That was the last question on your preview exercises. We created it that way. The absolute value of opposites is exactly the same. Okay, so students have learned different ways along the way to solve these equations, and sometimes they get you in trouble. The only thing you're going to change the sign of is the constant. Don't touch the expression inside. In other words, do you agree that I could write this, these two statements? Do you agree I could write these two statements? Okay. So all I'm going to do now is I'm going to say, all right, then if those two statements are true, then I'm going to take this 2x plus 1 and I'm going to set it equal to negative 11. Because I want to find out when 2x plus 1 is equal to negative 11. Why? Because the absolute value of negative 11 is 11. So I take that 2x plus 1 and I set it equal to negative 11. And then I take that 2x plus 1. Let me rewrite it right above this one. I take this 2x plus 1 and I set it equal to positive 11. So I took the stuff, which is really an expression. I took the stuff inside the absolute value sign symbol and I just created two equations. The stuff inside is either a positive 11 or a negative 11. And then you have two baby linear equations to solve. You get 2x equals negative 12, x equals negative 2 as one of your possible solutions. Thank you. And then you have 2x equals 10, x equals 5. And then you check it. You go back to your original statement, you put in a negative 6, and what do you get? Negative 12 plus 1 is negative 11. You've created it that way. You said, when does this equal negative 11? And that's true. And then you go back and you put your 5 in, and you check it. And if you hadn't noticed my mistake, I would have found it when I put it back in here. So that's why it's always good to check. And that works, okay? So all you have to do, the only sign you change, never mess around with the 2x plus 1, never change that. You're just pulling it out and you're setting it equal to either a positive 11 or a negative 11. That's all you do. So you don't have to worry about distributing negative signs through there or any of that stuff. Keep it nice and simple. Okay, so you got quite a few exercises to work on at your seats. You can work at your seats on the boards. Oh my God, we have a long demo today. All right. This is a new notation. Instead of using always the set builder notation to represent infinite sets, we're going to use something called interval notation, and it's pretty straightforward. Do I have a staple here? Oh, someone took my stapler away. I always liked. All right. Well, I just have to pretend. So how could we represent the solution set for this linear inequality, x is less than or equal to 7, on the number line? Well, yeah, Marissa? Yep. Ooh, it's less than 7, right? Yeah. Okay. Okay. So, right. If it didn't have this equal sign here, you'd have an open circle. And that's what you're used to doing. We're going to show you a new notation and a new way to represent that. When you include a number in your set, you're going to use a bracket. So instead of that solid dot, I'm going to put this bracket right here. It's like a staple. Doesn't that look like a staple that's vertical? And so you're stapling that number to your solution set. There it is, 7, and everything to the left of 7. So the way we would represent that set with set builder notation is right here. It's much easier to do it with interval notation, left to right. So it's 7 is your largest number that goes on the right-hand side, and you use that closed bracket. This thing goes to the left forever and ever, or to the left forever and ever. I could walk right through that wall, up to Vermont, up to Canada, to the Arctic Circle. It keeps going forever and ever. That's negative infinity. And since negative infinity is not a number, it's a concept, you use a parenthesis. That says I'm not including that. That would be just like an open circle if it was a number there. Okay. So the interval notation that represents this is parenthesis negative infinity comma 7. You always put your smallest quantity in the left-hand side of this interval and your larger number on the right-hand side. So sometimes we get intervals like this, staple 2 comma staple 3. How would I represent this on the number line? Well, I would just put a staple because I'm going to include the 2 and a staple at 3. And it's the infinite numbers in between. There's an infinite number of numbers between 2 and 3. You'd say, geez, it's such a small little interval. Really? There's infinite? Yes. We could keep breaking that down further and further and further, getting smaller and smaller. Well, I don't know if it's small or large. I don't know. That's a number theory question. Okay. But then we keep getting, yeah, we could get 2.999999, and then we could get 2.999999, and we could be getting 2.5, 2.49, 2.4. I mean, we could do this forever, right? Yep. There you go. Okay, so square brackets means both of those endpoints. These are the endpoints. 2 and 3 are called the endpoints, are included in the interval. When you have 2 parentheses, it means the -1 and the 5 are sort of setting up the idea of how far you can go, but they're not going to be allowed into the set. So -1, open parenthesis, and 5, it means everything literally in between, but they're not included. It's called an open interval. So you would be used to putting open circles at -1 and 5, like Marissa told us earlier. Then sometimes you can get intervals that have one side with a bracket and one side with a parenthesis. And that means I'm not including the -4 here, but I am including the 1, and I'm every number in between. but I could be the number 1, but I'll never be a -4. I'll get as close to -4 as possible, but I'll never be -4. And these infinite intervals, if you are going to the left like we saw in the first case, you put -infinity with a parenthesis. If we were looking at, say, this interval on the number line, that would be starting at 10, including the 10, and going to the right forever. Okay? You always use parentheses with the infinite set. So the reason that these are really important is when we solve inequalities, which is the next thing you have on your paper. The only thing you have to remember, the only difference between solving an inequality and a linear equality is that whenever you multiply or divide both sides by a negative number, your inequality, the direction of your inequality reverses. So the only way to solve this is to divide both sides by -4. So you get x here and -2 here, and you must change that direction to this. So x greater than -2 can be represented by this set. You help me. I'm going to have a -2 and I'm going to have an infinity. And what do I use here? Do I use any brackets, parentheses? Parentheses where? In front of the -2 and after the infinity, right? So that says every number greater than -2. So you have, unfortunately, only 15 minutes left to work on your class activities, but look it over and maybe start with what you think might give you the most trouble and versus going 1, 2, 3, 4 like that. And I'm here to help you out. Huh? You can look at that in your textbook, okay? I think you can look that up over.